Okay, in the last video we saw that for our robot and effector to reach a desired point with coordinates A and B, the translation part of the transformation matrix should match these coordinates A and B. In other words, the x component of the translation vector should match A, and we get this equation. And similarly, the y component of the translation vector should match B, and for that we get this equation. 0.5 S1 plus 0.3 S12 is equal to B. So computing inverse kinematics for this particular robot basically means solving these two equations for values of Q1 and Q2. Remember that C1 is equal to cosine of Q1. Similarly, S1 is sine of Q1 and C12 is cosine of Q1 plus Q2 and S1 is sine of Q1 plus Q2. Okay, so let's go ahead and start computing. Okay, how do we go about this? In this particular case, and actually quite often, you will see a good trick to try is to square up the two equations that we are solving and then add them up. In this case, these two equations. Okay, so let's go ahead and solve these equations. Squaring and adding, we get a square plus b square is equal to 0.25 c1 squared plus 0.09 c12 squared plus 2 times 0.5 into 0.3 c1 c12. So we are finished with the first. And b square, for b square we have 0.25 s1 squared plus 0.09 s12 squared plus 2 into 0.5 0.3 s1 s12. Okay, if we go ahead and simplify these equations, after simplification we get a square plus b square is equal to 0.34 plus 0.3 times cosine of q2. Okay, we can further write it like this. Solving for cosine of q2, we get c2 is equal to a square plus b square minus 0.34 divided by 0.3. Okay, so we end up getting c2, a cosine of q2 is equal to a squared plus b squared minus 0.34 divided by 0.3. Okay, what happens next? Well, we have an expression for cosine of theta 2 or q2. We would be tempted to go ahead and compute q2, but before we solve q2, we have to consider a few cases that we have to deal with. Okay, so case 1 is, what if this whole thing is greater than 1? Remember that this is a cosine, and obviously it cannot, if this thing is greater than 1, then it cannot be the value of a cosine, because cosine can only have values between -1 and 1. So what is happening here? This means that we have no way to solve this equation. We have no way to solve this equation, this one. And what basically that means is that we have no solution to our inverse kinematics problem. the point that we are asking for is too far away from the origin, and the robot simply cannot reach it. The robot simply cannot reach it. Okay, what about case 2? If this whole thing is equal to 1, it is exactly equal to 1. Okay, let's start illustrating some of these. Okay, so if this is our coordinate frame, let me draw a coordinate frame here. This is my coordinate frame, and this is our robot. So this is my robot. All right. So there has to be some maximum reach for this robot, and that maximum reach would be when the two links are extended fully. Okay, and this would lead us to a circular region, uh, which the robot cannot exceed. A circular region which the robot cannot exceed. Let me just draw a circle to illustrate what I'm trying to say. We will have a circle. Okay, let's say this is the center of my robot. And we have a certain circle, and our robot cannot go outside this circle, and anything that is outside of this circle falls in case 1, falls in our case 1. And this thing is greater than 1. It means that we want our robot to go beyond this circle, which is not possible, because if it fully extend, these are the limits. It can reach up to this circle, that is the maximum possible it can stretch. Okay, so this circle defines a boundary or the extent of our robot arm. Outside of this circle we cannot access any point, so there is no solution. We have no solution, and there is no way of for our robot to get there. In this case, cosine of q2 would be equal to 1. This thing would be equal to 1, and which means that q2 equals to 0. This immediately tells us that q2 equals 0. Okay, so for case 2 we have q2 equals to 0. For case 1 we had no solution, or let's say we had 0 solutions. Okay, in this case, if we plug in the value of q2 equals to 0 in our original equations, these equations, if we plug in the value of q2 equals to 0 in these two equations, what we get is we get 0.8 C1 is equal to A, and 0.8 S1 is equal to B. This is what we get, and from this we can compute Q1 is equal to A tan 2 B comma A. Okay, because the 0.81, this cancels out when we are doing a tangent inverse, and we get the value of q1. So in this case we have exactly one solution. Let me erase this and make some space. Okay, so in case 2 we have exactly one solution. uh, and what does this mean? Well, if the point that we are asking for is exactly on the boundary of the circle of the workspace, then the robot arm has to be completely stretched out to get here. So you can reach any point on the circle. The robot can reach any point on the circle. It cannot go outside. Similarly, it can reach any point on the circle with exactly one solution. By one solution, we mean exactly one value of q1, because q2 is 0, the arm is fully extended. So q1 is variable, and it can have values between 0 and 2 pi. So any value of q1 between 0 and 2 pi would lead us to a unique point on this outer circle. So we have one solution for this particular case. Okay, one quick note about using a tan 2. In general, if someone gives you the cosine of an angle and says c1 is equal to alpha, right? If someone says that c1 is equal to alpha, then you would be tempted to write that q1 is equal to cosine inverse of alpha, right? But be careful with this, because that is not necessarily true. Remember that there are, in the interval 0 to 2 pi, there are multiple angles whose cosine equals alpha. The same thing is with sine. If someone tells you that S1 is equal to beta, then you would be tempted to say that Q1 is equal to sine inverse of beta. But again, this is not the unique solution to this. There are multiple angles in the interval 0 to 2 pi whose sine equals beta. So if you have only the cosine of an angle or only the sine of an angle, like these two cases, then you cannot uniquely identify that angle. However, if you are given both the sine and the cosine, then it is enough to uniquely identify your angle. And if you are given both of these, then our angle is going to be a tan 2 beta and alpha. That's what we had written. The solution would be a tan 2, this is a library function, beta and alpha. So a tan 2 is a tangent inverse function that looks at the quadrant that the angle should be in. It is offered by most programming language math libraries. But remember, if only the cosine is given, then there are multiple solutions for the angle. Similarly, if only sine is given, then there are multiple solutions for the angle. If both are given, only then we have a unique solution for the angle, and that is specified by a tan 2, which is what we used here because we have both the sine and cosine for q1. All this discussion was pertaining to case 2. Okay, case 3. If this term is actually less than 1 but also greater than -1. Now we have cosine of q2 which equals something that is between -1 and 1. So then q2 can be cosine of inverse, cosine inverse of this thing, right? But be careful, because it can be 2 pi minus the cosine inverse of this thing as well. There are two angles in the interval 0 to 2 pi whose cosine equals this. So we have two possibilities for Q2. In case 3, we have two possibilities for Q2. Q2 is equal to cosine inverse of this whole term, cosine inverse of this whole term, right? And there is another possibility that Q2 is pi minus, again, cosine inverse of this whole term. So for each of these two possibilities, if we plug them back into our original equations from the previous page, these two equations, if we plug the two values of cosine, two values of Q2 in those equation, we get two unique values for Q2, two unique angles or theta values for Q1 and Q2. So in this case, we will have two solutions, and that makes sense, right? If the point that I'm trying to move towards is strictly inside, it is inside my circle, in this circle workspace, then there are two ways for the robot to reach it. Okay, let me illustrate what I'm trying to say. Okay, let's say if this is the point that I want my robot to move to, then there are two possibilities. I can have my robot arm like this, or I can have my robot arm like this. Okay, these are two configurations. One is called elbow up, or one is called elbow down. So we will have two possible solutions. We will have two possible solutions for our case 3, because Q2 can have two values, and these two values would lead to two solutions. Okay, case 4. When this thing is equal to -1, this is case 4, then what we are going to have is Q2 equals to 180 degrees or pi. Okay, only because if Q2 equals to pi, only then this expression would become -1, right? So this means that Q2 equals to pi, and again we are going to have a single possible solution. Only one solution exists now, which we get by getting the cosine and the sine. So in this case, we end up once again with just one solution. Okay, what is going on here? Well, what is happening is that there is also an inner circle. Let me illustrate this inner circle in a moment. What we have is an inner circle. Let me grab a circle and draw it. Okay. Okay, so what is happening, that we have an inner circle, and if the point that I'm trying to get to is on the boundary of this inner circle, then the arm, in order to get here, has to be fully bent on itself, right? This segment of the arm will have to be fully bent on itself like this. Only then the end effector can reach a point which is exactly on this boundary. So the first link has to go out and the second link has to come all the way in. The second link has to come all the way in, bend on itself. So in this case, Q2 is going to be pi. And then that's the only way that we can put the end effector on the boundary of this inner circle. So Q2 has to be pi and then Q1 is uniquely determined. Okay, and finally we have case 5. This is case 5 when this thing is less than -1. In which case we have this is less than -1, and now obviously we don't have any solutions because cosine cannot be less than -1. Now we are asking the robot to go inside this little circle, and there is no way for it to get there. It bends all the way on itself, but there is no way it can get even closer to the origin. So it is impossible to get to. Now if we look at the entire picture, we see our 5 cases. We can write 0 solution here just for completeness. 0 solutions. Okay, so we have these 5 cases. Outside this bigger circle, no solution exists. The robot cannot reach it, cannot reach any point beyond this outer circle. On the boundary of this outer circle or the bigger circle, only one solution exists. And the only way for the robot to get there is to fully stretch out. Between these two circles, we have 2 solutions for each point. For each point between these 2 circles that we want to go, we have 2 possible solutions. There are 2 ways for the robot to get to every point. Okay. We discussed an elbow up approach and an elbow down approach. And what about the points on this inner circle? Again, we have only a single solution, and the only way for the robot to get there is to be fully bent on itself. If this outer arm is fully bent on itself, then we can get to the point on this boundaries. Inside the inner circle, we have 0 solutions. There is no way for the robot to get here. So this robot has what we call a workspace, and in this case the workspace is shaped like a donut. This is the workspace of our robot. Strictly inside the circle, inside the workspace, it will have 2 ways to get to every point. On the boundaries of the workspace, the outer circle and the inner circle, it will have only a single way to get to each point. Outside the workspace, it has no way to get to where we are asking it to go. This is a very common behavior. Almost every robot essentially has a workspace. Inside the workspace, there will be 1 or more solutions to the inverse kinematics problem. On the boundary of the workspace, the number of solutions go down, and outside the workspace, the number of solutions is exactly 0.